Excellent.
So yesterday we talked about the first 3 problems on the test, the ones that are quantitative. Today we're going to talk about the last 4, which are all kind of short answer, draw a picture kind of problems.
You're a natural.
I love my first instinct is to do like the Sunset Boulevard.
Yeah.
Close up.
Now your hair's all sticking up.
It's gonna be stuck in my head for the rest of the night. Thank you so much. Alright, that's better.
Anyway.
Oh God.
Forces. So we talked about a lot of stuff with forces. We're just literally repeating the footage that we didn't get to film last time. We talked about a lot of stuff before. We talked about Newton's first law, we talked about Newton's second law, we talked about free body diagrams, we talked about when things are balanced or unbalanced. So, the stuff that we're going to focus in on for the test is Newton's first law and free body diagrams. Who remembers what Newton's first law says?
If something stays in motion, it's like stays in motion. And if it's at rest, it's
Unless acted upon by an outside
They're all
force.
trying to say it at the same time.
That's good.
I think O'Brien
I can
may
parse
even
like 7
say,
things at once. So Newton's first law, an object in motion tends to stay in motion, an object at rest tends to stay at rest unless acted on by a net external force.
Yeah.
In other words, and slightly more useful words, if I've got an object and the forces acting on it are balanced, so there is no net external force, then that thing is either at rest and continuing to be at rest, or in motion and continuing to be in motion. By that I mean not speeding up, not slowing down. That's what it means that the forces are balanced. If the forces, on the other hand, are unbalanced, then this object that's at rest will no longer stay at rest and will start moving, probably speeding up, because quite frankly I'm not sure what happens if an object at rest slows down. It's a little confusing. Or an object that's in motion will change its motion. It might speed up, it might slow down, it might go backwards, change. So that was the idea with kind of balanced or unbalanced. So, talking about Newton's first. Which gets us this idea of balanced or
okay.
unbalanced forces.
Natalie cut herself.
I think I found
What's
this
this
one.
With what?
With the tape.
Wait, what?
And it feels.
We've had knives around for weeks and you cut yourself on the tape?
Natalie, want some Neosporin on that?
Oh yeah.
Ow, it burned.
Then put the Neosporin on.
I'm gonna wash my hands.
Yeah, it's a good idea. Alright, what were some of the kinds of forces we were talking about?
I don't even know.
Balanced and unbalanced.
What?
Friction.
Specific things. So we have
Oh.
friction,
Oh, spring tension.
Yeah.
we had tensions, which were slightly different than springs. Any other forces we had?
The one
Kinetic.
and
Kinetic was an energy.
Oh, wasn't it the gravity?
And we had normal, we had gravity.
Wow, I do not remember this.
We had some real gravity in this situation if you don't remember things. The general rule for forces, all of these are nice and they're all kind of shortcuts for remembering, what direction things act in. But the general rule for a force, if you're stuck on this, every force can be written as on something by something else. So when in doubt, the force on the eggplant by the calliope.
Are you going to use fake things on the test?
An
For the-
eggplant?
Those are not fake things.
Like, I know
You really don't. Do you guys have a
And you're
kaleidoscope
like
on an eggplant?
12 gobs.
If you had an eggplant resting on a calliope, then the normal
What
force
is a
would be,
calliope?
it's like a circus organ.
That is so
Oh,
weird.
yeah.
They used to have one in
This isn't the
Honeywell
first time we've
that never
discussed
got
a calliope.
colitis.
No,
Yeah, it is.
It could very well be that calliope will be one of the questions in the last problem.
So you're going to be asking
In the
what a
last
calliope
problem.
is?
Maybe
not the
maybe
forces.
the last part will be, questions, comments, concerns, queries, fill in 7 or 8 others from the course of the year.
Koalas, caterpillars,
Oh my god, that'd be so smart.
Cake.
coconuts, coconuts.
Anyway,
What are those little things that hold skin together?
Band-Aids?
If that was the
No,
question.
they're like.
Codes.
Splints.
Okay.
Oh.
Sorry.
So this was part of what we did. How did we represent these forces?
Those like charts, L charts.
arrows.
That was energies. Arrows. So how did we organize the arrows? What do we call
Free
them?
body diagram.
Free body diagrams. Which is not something from the 60s.
I don't get it.
What?
You'll understand it when you're older. What were the rules for free body diagrams. How do we know how to draw these things? What do we do?
Can we condense it to a little dot?
Yeah. So let's say I have a car. Just true. I do in fact have a car.
Good for you. I would hope you knew at this point in your life.
So this car, well, I mean, I just like taking public transportation or like.
True. Very true.
So this car gets pushed down into my dot,
Okay.
right?
Sure.
What forces are acting on the car if it's just kind of sitting on the road?
Gravity.
Normal.
Gravity and normal. What direction is gravity?
Down.
Down. Gravity is always down unless we're in space or somewhere where the curvature of the Earth is avoided. Normal force. Normal force is which direction?
Up.
Up.
Or no, perpendicular to the gravity.
Well, perpendicular to the ground, which in this case is up.
You know.
Are these forces balanced or unbalanced?
Balance.
How do we know?
Because there's
Because the car, well, even more than so than it's not moving. It's at rest. That's the not moving bit, but it's staying, right?
Yep.
That's the important. We have to be careful because things can be moving and have balanced forces. So if you remember the problem from the homework where somebody was pulling a chest across the ground at constant speed,
don't touch it.
that's in motion and staying in motion. So that's still balanced forces even though something is moving.
I thought it was just that the arrows were like down each other.
But how do we know if the arrow should be? Oh, there's Woody.
A length.
She just ran by.
Who?
Woody just ran in, I
Oh.
Like down there on the ground.
think. Yeah. Or someone who looked a lot like Woody just ran into the school parking lot.
Wait, where was Whitmore?
Apparently running, like sweatband, like
Oh.
sportwear, like.
Oh, I thought she was like in her normal clothes.
No, just running and like the dogs are chasing her and the sirens are going.
Wait, she has like a sweatband on. She's like running.
She was running, literally running.
Running? Did you get that on
Let's get
camera?
back to the.
Yep.
So anyway,
Like, did you get Winnie
The
on
camera sees everything.
All right.
Oh, no, no.
it's not so.
I can't.
These
The window's over there.
arrows would represent the balanced situation, but let's say that it was unbalanced. Let's say instead of this being a normal car, it was in fact a rocket car.
Okay.
And so my car was preparing to fly up into space and was speeding up. How would this be different?
There would be another arrow pointing to whatever direction.
There'd be another arrow pointing.
Oh my
There'd be another arrow pointing.
Wow.
I guess I don't really call people that often now that I think about it.
I raised my hand all the time though. But I was gonna ask if it's taking off straight from the ground or if it's like is like the DeLorean that has to go 88 miles per hour. Yeah, so you have to like
The
feel
DeLorean only has to go 8 miles per hour to travel through time. Technically, the DeLorean in Back to the Future 2 is capable of like rippling up into anything.
Okay, I have no idea what
Oh, I thought it was
Can we
Let's
stay-
Anyway, point is we need another force, right?
Yeah.
Okay, if it's lifting straight
Some
up.
kind of rust, maybe.
You would be like dripping boat if you
Wait,
And
but that's not.
presumably-
Wait, that's not on the list.
True. Also, it technically wouldn't have a normal force anymore, but
Yeah, they
so
have
there'd be
that.
some, let's say, push from the engine. In this case. So, unbalanced because accelerating upwards
Wait, but it would also
from engines.
would it also have like FM?
Not once it leaves the ground.
So
if
that's
we're
only for
taking
things
off-
from on rep, like that.
Yeah. All right.
No, it's not. It's not common.
We okay with this?
I got it.
Unbalanced.
Well,
Yeah, but
is
you
it at
can't
rest and
see it.
staying at rest or in motion and staying in motion?
Oh, wait. So where does it start? Is it still on the ground when you start?
This is apparently as it leaves the ground.
So it's moving.
Yeah, it's beginning to move. Yes.
But his front was. So it's not balanced, but it is balanced.
So, presumably my rocket ship is speeding up as it goes up.
So it's accelerating.
Yes.
Okay, then it's not.
So
balanced.
they're not balanced. Next question. Number 5 on energy.
I hate everything.
Okay then.
Even One Direction.
Oh, snap.
That was great.
Nicely done.
I'm excited.
Oh my god.
That was hard.
There's no such thing as a skin holder.
Like
They're like
gauze?
white. They look like this.
There are little things that
Get
this on camera
Those
too.
are called butterfly bandages.
I got it.
You don't need them.
Natalie, you need that if you have like a serious injury.
If it like is close to stitches.
She just asked
All
if she
right.
needs stitches.
As much as I'm concerned for your gross bodily injury, final exam.
Natalie, put a regular band-aid on it.
There's no band-aids.
Yeah, that's.
Mr. Russell, what kind of show are we running here? Why aren't there any band-aids?
Yeah, you had knives and
I can assume they were used.
You have the knives without the band-aids.
You have knives. In the
And no one
closet.
cut themselves with the knife.
I cut myself today.
Do the thing.
So, what kinds of energies do we talk
I'm
about?
doing cut herself with a knife.
Like,
What? We had kinetic energy.
Wait, I heard that there were no LOL diagrams on the test. Is that true?
That is correct.
Let's try to
Score.
keep going and
What other kinds of energies?
Thermal.
Thermal. What else?
Everyone's on the phone. I need to get a band-aid.
Potential.
What kind of potential?
Electric potential.
Chemical potential.
no, that's
Alright, well, we get chemical.
Ask Miss Richards.
Gravitational.
Gravitational potential.
And you probably don't have band-aids.
Well, she probably will have because they would have been used.
Oh, we already have elastic.
We do not have, we have electric.
Oh, elastic.
So elastic works. What did we call elastic? We used the E or S?
I thought it
S, because for like spraying it.
No,
Did we use E?
I think we used EL.
No,
Yeah,
EL is
EL.
electric.
Oh.
we didn't do electric, I thought.
We'll make that E.
oh my god.
We kind of talked about electric energy when we get to circuits.
Did you get one? Yeah.
Any other kinds of energies we mentioned, talked about, discussed, brought up?
Wasn't there
Perhaps
like
philosophic
spring
about?
tension?
Elastic.
No.
A spring potential is an elastic potential. Anything else?
When it's gravitational potential, does that mean if it's off?
Like if it's on a hill or something.
Yeah,
Like
if
it
it
has
has
the
some place that it
possibility
could
of going
reduce its height.
Okay.
Technically, all of these are potential energies, but gravitational potential, I just want to everybody tends to get hung up on potential energy and say when they mean gravitational potential energy. So I just kind of wanted to, yeah, just set that one
Is
aside.
Winnie
What?
just not coming? She's just running.
She's not actually in this class.
She's always in here though. I thought she
She's
was
always
in this.
right here. Sam, do you want to get to the LOL diagrams or not?
All right.
We're not. There are none.
But he
How
just
did
said the words.
how did we bring these things together?
Wait.
Use LOL diagrams.
All right, what was the point of these LOL
But I
diagrams?
thought there were no LOL
Yeah, you
diagrams.
just said
Doesn't mean that it doesn't hurt to remember what they were.
To represent
What was the point?
transfer of energy.
The input versus output of energy.
So we had some initial energy, and then stuff went in or out of the system. We called that what?
Work.
Work.
Maybe.
So work was energy going in or out of our system. What was the whole point of these LOL diagrams? What were we using to kind of sort out if we had done them correctly or not?
It has to be
Oh.
equal.
What had to
What
be
goes
equal?
in and what goes out? Like,
Alright.
well, technically,
What was the
you
guiding
lose
principle?
things, though.
Yeah, I had
Yeah,
to
right.
You
do
can't
that.
create or destroy it.
So,
you can't create or destroy
All
it.
that's coming back to this idea of the first law of thermodynamics.
Are
Right?
we only using Newton's first law?
Yes.
Energy cannot be created or destroyed.
Energy can neither be created nor destroyed. It can only be transferred from one form to another within a closed system. Unless you bring energy in or out of your system by doing work. Algebraically, we said that this meant that the final energy was equal to the initial energy plus whatever work we did. Or that the change in energy of our system was equal to the work we did. If we put energy in, did positive work, the change in energy was positive. We ended with more energy than we started with. If the work was negative, we took energy out of our system, the change in energy was negative. We ended with less energy than we started with. That was kind of the whole point of these LOL diagrams, was to kind of organize this idea. Yes, Susan.
So we can take energy out of the system. We have to just account for it in the
Correct.
circle part.
We can't destroy energy. It's like a Lego set, basically, was the analogy. Where are my keys?
Oh boy.
That was weird.
Is that like a safety blanket or something?
Well, it's really they're in my pocket all the time.
We're
and they work.
lopsided because you didn't have your keys on one side.
Just leaning this way slightly.
So what was it?
Are those
So-
like green spots on your hand?
Yeah, I don't know what they were.
Here's the green ink.
So let's.
So point was, you can think basically if you have a Lego set, right? It's got 100 pieces or something. You know, it's always going to have 100 pieces unless you've lost some of those pieces.
We're added pieces.
You're not going, or added pieces. You're not, the pieces aren't going to spontaneously disappear.
Okay.
Except that it turns out that you could spontaneously destroy a Lego piece and reduce the amount of Legos you have, and you know, release it as energy, or in this case, change the amount of energy you had and spontaneously created a Lego piece.
Or you could just lose the Lego piece behind the couch and never be able to use it again.
Correct, but but the Lego piece is still there.
Yeah.
Well,
It's
but then-
just no longer in your
But then
box
if you
of
break
Lego
the Lego piece, then it's just in pieces and you can't use it, but it's still there.
Dude, you know how hard that is?
Yeah, I was gonna say, I would you try to break a Lego piece, so serious.
Can you make
Yeah.
this glass?
Couldn't you use a laser? Okay.
Reasonable?
Yeah.
No, you couldn't.
Last, well not last, sixth question.
That was like, so we don't need to know anything other than that for energy?
No,
Like butterscotch.
there's no numbers on energy, so there's nothing on like knowing that kinetic energy is 1/mc squared or gravitational is mgh. None of that. Last one is on or not the last one, the sixth one is on relativity. And we said there are two types of relativity that we talked about. We talked about special relativity, and we talked about general relativity, which are wildly misleading names. That they tell you nothing. Yes.
Is there gonna be like a problem with relativity, or will you just have this like what?
Do you not remember all that worksheet that you did, full of like Lorentz transformations and like determining the time dilation?
What is this, a joke?
No, I did not.
Because we didn't have it.
Good. Mr. Howell, you can't say stuff like that to me.
I actually got scared there.
Mr. Howell, you don't even know how much pressure I'm under to get a 5 on my A-push exam. You don't even know. What?
No, all that we did for special and general relativity, we talked about them in a very conceptual way. So we talked about special relativity. We talked about what the postulates of special relativity were. Anybody remember what we said?
What's it? Time is, or like, time is relative or something?
That was one of the results, kind of. But what goes into special relativity? What was kind of the like?
Something
Ooh,
about
I know.
motion.
Oh, I just read it on the book.
Oh, there's no preferred point of motion.
Kind of.
The speed of light is a constant, and there's no preferred reference frame. I just know
Speed of
that.
light is a constant.
Oh, you're so proud of yourself.
Yeah, I am.
Yes, Susan.
I don't really know what's up with my
Was that like the only time you took
capitalization, but
notes
we're
this
just
year?
kind of going with it.
What?
Was that like the only time you took notes?
No, I took notes a couple times. Look, I took notes on waves, which should help me during the exam on waves, but you know.
Do we need to know about waves?
Wait, why is the speed
We have
of
gone
light?
through the entire test at this point, aside from the
Like
10
8
random
different
questions.
Wait, why is speed and light constant capitalized?
Because I kind of got carried away.
Capitals are so overrated.
All right.
And then the second
So,
one isn't capital.
At the start of the 20th century, a whole bunch of scientists had basically a couple of questions left in physics that they thought they had to answer, and then it turns out they were wrong.
Yeah.
But one of the things they were kind of struggling with was this idea that they thought the speed of light should depend on how you look at it.
Oh, is this just for special?
Yes. But they kept saying, they did experiments after experiments and found no variation in the speed of light, no matter how they made these measurements relative to a beam of light with their motion. So Einstein comes along and says, all right, let's say the speed of light is constant. Let's just take that as it is. And let's say that the laws of physics are going to behave the same way no matter how we're moving relative to each other. So if I'm in a car, throw a marker up and down, I see a marker go up and down. If I'm in a car and you guys see me going by throwing a marker up and down, you see a marker go up and down. There's not a right answer to this. Both of the two pictures are consistent with each other. The motion depends on our relative motion. The motion of the marker depends on our relative motion. Turns out that all of physics kind of behaves that way. Things act differently depending on how things are moving relative to each other. So we saw this with the example of the guy in the train and the guy outside the train. Lightning bolts on the two sides of the train. The guy outside says, my goodness, he's lightning bolts. They've struck the train simultaneously. The guy in the train says, no, the one in the front struck first. They disagree on what it means for these things to occur simultaneously. There's no longer this idea that, two things happen at the same time, everyone agrees they happen at the same time. Your motion through space distorts your perception of time. And there are kind of two major consequences that we had wrapped up with this. Anybody remember what we discussed?
Time is relative.
run slower.
Moving clocks run slower. Time is relative.
So if I ran around with the clock, would it move slower?
If you ran around with a clock, it would be imperceptibly slower than a clock which was not moving relative to you.
But it actually would be tiny.
Well, I don't
tiny.
understand that at all. I don't, you running with a clock.
So basically, you can move through space. You move through space-time at the speed of light. Light entirely moves through space at that rate. So a beam of light doesn't age. It doesn't move through time at all. We tend to move through time more than we move through space. We move pretty slowly through space. But the faster you move through space, the slower you move through time.
That's so weird.
Yep.
All right, Amanda?
But but like, well, 2 questions. Moving clocks run slower than what? Like it's
Ones that aren't moving.
Okay, and then the other thing is like, how can we know that? Because we never have a clock that is not moving. Because Earth is always moving, and the clocks are
But
on
a clock
Earth.
moving relative to a clock on Earth is moving faster than the clock on Earth.
Okay.
All right, so we can think of the clock on Earth as being at rest, and the other clock is moving relative to it, and we can conduct our experiments like that.
Okay. But what if you were on the International Space Station and you had a clock next to you and you're holding it in your hands? Is that
They've done
not
this.
moving?
There are clocks on the International Space Station, and they run at different rates than clocks on Earth.
No, but then the clock
How
on
do
Earth
they
is
know what
moving
time it
relative
is
to
at
you.
Earth? Like
Because
how
they know exactly how to calculate a second on the space station relative to a second on Earth.
But then would
They
The same sense,
internet.
like, yeah,
How do you get internet on space?
the same way you get internet on your phone with a satellite.
That they can reach over there?
The satellites are
Over where?
The satellites are
up in
possibly closer to the
Oh.
space station than.
Yep.
Here.
Oh, I thought they just had like those. Yeah, never mind. Not that.
All right.
Yeah.
Does that also work for cell phone clocks?
Yeah, I mean GPS
Yeah,
systems
that's
in
what-
general require these relativistic corrections to function. They have to have this degree of precision that the rate at which time flows differently on Earth versus in orbit, it's important. Amanda?
Is that why they had to do the GPS project last year?
No, that was just something I thought was fun.
So much better than bridges.
No,
bridges
Alright.
are better.
still
The
better.
other
No.
consequence of special relativity, anybody remember?
Wasn't it that? Oh,
Time
length
is
is relative.
So this is time. We got relative time here, but lengths
Don't
also.
matter.
Moving lengths or moving rulers
I
are
remember
shorter.
Bob's book.
Oh, yeah.
The barn and the ladder.
Yeah.
Yeah. Yep. Nighthawk Ormings.
Yep.
There is, so basically the way that this works, things that are moving are short. So let's say I had 2 rulers, all right? And these 2 rulers, when they're at rest, are the same length, both meter sticks, all right? So I'm going to take one ruler and I'm going to put it out here and have it just kind of chilling in front of me. I'm going to take a second ruler and send it flying by at like 80% the speed of light. And what happens when these 2 rulers pass each other, I see that the moving ruler appears shorter than the stationary ruler.
It is shorter.
It is shorter.
No, when they're at rest, they're both perfectly good meter sticks.
Uh-huh.
I don't really have a future as a magician.
Different size.
It's just 2 meter sticks, right?
I'm sitting over here.
Anyway, that's the basic idea. That's the whole idea with that barn paradox. And really, it comes down to an idea of simultaneity. The idea is that if they're the same length, then
Wait, say that
If I-
again.
simultaneity. The idea is that if I look, that both ends of the meter stick are at the same spot at the same time. But the idea of the same time is weird when things are moving relative to each other.
Basically, if there's a clock attached to the end of the moving meter stick and to the non-moving meter stick, the clock of the moving meter stick would be faster.
Oh my
and
God,
the
don't
meter stick would be
confuse me.
slower.
No, the clock on the meter sticks run. The clock on the meter stick is slow, and the meter stick is short. That moves relative to mine. So
yes,
yes.
compared to the one on the not moving meter
Yes.
stick.
They're
Yeah.
not awkward.
All right. That was the idea of special relativity. With general relativity, what was the idea here?
Ooh, I know.
Yes.
The cat in the box.
That's Schrodinger's cat. What are you talking about? Okay. This is gravity can now bend light,
All right, that's part of it.
i.e., gravitational
Space
length. I don't know what that
is
means.
warped.
Are these postulates?
You know what?
Yes, or gravity equals slower clock.
All right.
Space
General
time
relativity is
warped.
basically a new version of gravity. Our old version of gravity was Newtonian gravitation. How does Newtonian gravitation work?
The objects have a mass that pulls each other to each other.
Yeah.
The
So
attraction.
the old picture was that masses attract each other. Mass attracts mass.
This is the fake one.
Well, no,
Like it's a false one.
it's the old one.
So it's not true.
I mean, it's pretty true.
Almost.
It was true enough that no one noticed for almost 300 years that it was wrong.
But it's still wrong.
Yeah. I mean, so is general relativity properly. It's just less wrong.
Then why
All
are we
of sci-
learning about it?
Because it's the rightest thing that we have right now.
But then what's the right thing?
We don't know.
That's what we're training you guys to find
But
out.
what's the
Train like actual
All of science is searching for a less wrong answer.
But what's wrong with it?
That's actually. Let's
That-
find out if we keep reviewing, and then we'll
All of
see
science is
maybe.
If we keep
It's going to be a
reviewing
long
it
time
past
before I
our
can
final.
convince you what's wrong with general relativity.
That's the
So?
definition.
Alright, the big thing that's wrong with general relativity is that it doesn't work on insanely small scales. You can't use general relativity to predict what happens inside of an atom. The theory blows up.
Oh well.
I don't know.
How does general relativity work? It's the old way that masses
Space-time
attract.
warp.
Yes, mass warps space-time.
You actually believed.
Mass force, space time.
Yes. So the picture here, right, we had a sheet. We think of that sheet as being space-time. If there's nothing in it, it's flat.
Song, the time warp
Yeah,
song.
sheet.
Oh yeah, that's the
Alright.
tablecloth.
Then if we put something in the tablecloth kind of sinks around it. That's what's happening, is that a mass in space-time warps space-time around it. So now objects that go near that mass take a different path. They curve along the now warped space-time. Yes, that's getting there. Yes.
You said so space-time, whatever, warps around the object?
Yes.
So what happens when the object
Did you cut yourself too?
And space-time unwarps.
Does it warp back?
Yeah, that's what they, basically that warping is what they call a gravitational wave. That's, there are things on Earth that they're trying to detect these.
Rachel cut herself.
Oh my god, guys!
I've been sitting here taking the tape off for like half an hour and she cut.
But it warps back to
I'm
the
getting real
Earth.
tired of me.
Yeah, it goes back to being flat.
I was bleeding.
Although, I mean,
You
maybe it
try.
gets like warped or something. Like if you stretch a rubber band too many times. I mean, we don't really, that would require like destroying and creating stars in the same spot, which isn't exactly an experiment we can readily do.
What do you want me to do?
What are some consequences of general
Wait,
relativity?
is that where that song comes from? That
From
black
Massive
hole.
Black? No, that's Rocky Horror Picture Show.
Like the let's do the time.
Yeah, that has nothing to do with
Black
relativity.
holes.
Okay.
That's transvestites.
And orbits.
Go off that.
Turns out, contrary to popular belief, transvestites, relativity, different things.
Guys.
What is
Yes.
I
What kind
had
This
a
is
question.
close.
black hole?
Good.
Alright, so one of the
Good job.
big things, the consequences of general relativity are black holes.
Susan, don't get injured.
I'm not getting injured.
Places where
I'm a
you
grown
have
up.
such a very dense object that it's warped.
You're a
space-time
year
density,
older than
pinched
us.
it down
You're
to a
like
point.
3 months.
Guys, I'm trying to review for your finals.
We're trying
If
to
you
solve
stop
this.
lacerating yourselves on aluminum tape for just a
I'm
minute.
gonna hold
I'm
this.
taking the tape off so no one hurts themselves.
Okay.
Until you
What are some other consequences of general relativity?
Orbits
I mean,
of planet?
that happens anyway.
That it's not actually true.
What?
It's not actually true.
That thing's orbit?
No, general relativity.
It's not absolutely true, but it is the truest thing we've got.
It's got lots of
So what are
I don't know.
anything else? So with black holes, why are black holes black?
Because you
Well,
can
can't see
catch
the
up
light.
light.
Gravity is so strong.
Yeah, so all of a sudden gravity can affect light. Light is a massless thing. Photons are massless. So under the Newtonian version, mass attracts mass, gravity does nothing to light, because light has no mass. It's light. Yeah?
I got it.
But now,
Another one of Mr. Avala's hilarious jokes.
that's right. Hilarious.
It was
Now a little too
excellent.
sarcastic.
What did you even say? I didn't even hear.
Aha ha.
So gravity can bend light. That gets us that's part of what goes into a black hole, gets us this idea of gravitational lensing. We had one other consequence we talked about of general relativity. Anybody remember? So we also said that general relativity, that gravity could affect clocks.
Oh yeah, that's
Yes, it does something to them.
it makes them go slower.
Or slows them
Oh,
down.
was this, like the thing with the twins?
That was special
Yeah, that's
relativity.
Wait, what's a paradox for this one then?
There's not really a paradox for this one.
Oh yeah, the twins go into space. What was that about?
One twin goes into space, one twin stays on Earth. The twin going into space moves really, really fast, so the twin ages slower. So when they get back, the twin that went into space is younger. Of
If
course, the
I had a
paradox
twin,
is
I
that the
would
twin that
do
went into space sees the twin on Earth run away really, really fast. So the twin who went into space should expect the twin on Earth to have aged slower. So when they both come back to Earth and the twin that went into space is young, everybody's really confused.
Have they tried this?
With twins?
Yeah.
No.
They can't go.
They've done it with they've done it with identical atomic clocks, but like the best we can get is like nanosecond variations with modern spaceship, with modern airplane flight basically.
If I had a twin, I would do that. I would make
You
them go
would, you would
into
also
space.
need something that could accelerate you to a high fraction of the speed of light.
Well, I'd make my twin create that. And I'd make them stay
So,
Anyways.
content-wise, this is the end of the exam. The last question, question 7, has 10 parts. The 10th part is kind of a wild card. It's a bonus. All 10 of these parts are kind of asking you to remember random things from the year. The first 9 of these are. The last one is just remember anything that's not already on the test and talk about it.
Can't worry, pick some.
So you can pick 3 of the 10 to answer.
Oh, okay.
All right? So they're talking about demos we did. They're talking about days that we kind of spend talking about random topics. They're all, you know, basically if there's something in your notes that hasn't appeared on homeworks, tests, or quizzes, it's probably in this question.
Like the
I
eye.
don't usually take notes on that stuff because I think it's just random stories.
Mr. Rahula, what was the purpose of the tablecloth thing that you did?
So that was an example of Newton's first law, basically. So if we pull out the tablecloth very smoothly, you know, if we do it fast, then there's like a little tug on the table, on the plate, the tray, the bottle, whatever. So there's very little force acting on it. So everything like wobbles a little bit if it's rough, but then doesn't go anywhere. If you do it poorly and there's a bump or something and it pulls, there's a force, the thing tips, you know, slides, spills, whatever.
I want to write about that.
What other demos did we do?
We played with the Van de Graaff generator for a day.
Amanda, can you explain that?
So the Van de Graaff generator has a belt in it.
Mm-hmm.
The belt is going around, kind of up and down here. At the bottom, there's a little kind of fuzzy thing.
Mm-hmm.
So as the belt goes around that, it's like rubbing your foot on a rug. You slowly begin to build up charge. So charge builds up on the belt,
Mm-hmm.
then goes up to the top, and there's a metal bar on the top connected to the sphere. It's like touching a doorknob then. The belt zaps the sphere, charge jumps off, and charge slowly begins to accumulate on the sphere. So then if you bring your hand near it, it jumps from the sphere to your hand, and everybody then screams.
Okay.
Or if you have your hand on it, it spreads out over you and your hair sticks up.
This video will be on like Kaiku, right?
It'll be on YouTube.
Okay, then I'm just gonna like watch that and
Okay? Alright. Questions, comments, concerns, queries, conundrums?
Miss
Last time.
Dr. Fidel used the word conundrums today.
Caterpillars and koalas.
And you guys should have known what it was.
Oh, what was that organ type circuit?
Calliope. Alright. Have a very good weekend, everybody.
Can we talk about that? So the last question we talked about conundrum.